again, good morning and welcome to Abaqus Technology Enhancement Updates webinar 2022. We will begin the session by a brief introduction of our speaker, Mr. Raghavendra Banchor. Raghavendra has over 15 years of industrial experience in engineering consulting, customer support, and technical sales in the area of finite element analysis, based design, and validation. He worked with Dassault Systems Simulia and MSC Software for over a span of 10 years. Working with the Dassault Systems Simulia brand, he has built deep expertise in Abaqus and broader Simulia product portfolio. Raghavendra holds an MTech in Mechanical Engineering from Indian Institute of Technology, Bombay, and his expertise is in nonlinear FEA, composite, and crashworthiness optimization, lightweighting, and nonlinear multiscale material modeling. With this, let us begin our session. You all are free to ask your questions to our speaker, and you can write them down in the chat box. We will address them towards the end of the session. Thank you, and over to you, Raghavendra.
Yeah, thank you. Okay, can you hear me? Hello,
Yes,
can you hear me?
Yes,
okay.
Yes, you're audible.
Yeah, so let me share my screen. Just let me know if you can see my screen.
Yes, it's visible.
So, okay, perfectly fine. That's great. Okay, just a minute. Yeah, so good morning, everyone. My name is Raghavendra, and I would like to welcome to this webinar, Abaqus 2022 Technology Enhancement Updates. And I would also like to thank you all for attending this webinar, taking out time from your busy schedules. So here we go. We have this is the quick agenda of our webinar. So it will run around 40-45 minutes, and then we have the question and answer session at the end. So I will begin with a quick company overview, and then we'll move to Abaqus 2022 updates, and that includes the structural mechanics and the material enhancement in the latest version that we have, Abaqus 2022. And then we'll move to the contact, what are the new enhancement, the feature that we have, and then we are going to see the high performance computing enhancement that we have, and lastly we'll look into what are the new features we have added in Abaqus CAE as well. So as a company, or we're Abaqus YS3D is an engineering organization. It has a multiple industry experience, starting from the high-tech, CPG, oil and gas, petrochemical, nuclear, aerospace, automotive, so on and so forth. And its headquarters is in USA, Houston, USA, and we have office in Canada, Mexico, India, and Turkey as well. So it's an engineering organization. It has a very strong team. It consists more than 100 employees. Mainly they are either PhDs or master in design, manufacturing, structural mechanics, fluid mechanics, electromagnetics, optimization, and reliability. So this basically shows our strength in terms of the team that we have. YS3D is a Dassault System Platinum partner, and we provide software sales, support, training, engineering, and a PLM consultancy as well. So let's begin with the structural mechanics and the material. As a part of yearly enhancement, we normally have the general release at the end of the year. So Abaqus 2022 is already released, and it's there for the download. So if you have already downloaded, please start using. If you have not, then please try to download this new version. And here we are going to discuss what are the new things that we have added in Abaqus 2022. First of all, I mean, the enhancement that we have is related to the material, the properties. Now you can define as a function of material point information, and that is available both in Abaqus standard and explicit. As you must be aware that in Abaqus, as a field variable, most of Abaqus material property can be defined as a function of the a field variable, like the material property can vary as a function of the space, as a function of the coordinate system, as a function of the time that's there for a long time. So now what we have done in this new version is that you can define this material property as a function of material point, which is nothing but as an output variable. Okay, so in this one, normally what we used to have in earlier version is if you had to define the material property which varies with reference to these output variables, you had to write subroutines, right? Now, with this new enhancement, there's no need of writing a user subroutine like the USD FLD and so on and so forth. So on the right hand side, you will see one example, like if you want to define material property with a different plasticity, behavior, intention, and compression. Earlier, you had to write user subroutine, but now with this enhancement, you can do it without using subroutine. So here is the keywords that is a standard keyword for material, star material, and the rest of sub option that you have: star elastic, star plastic. And what you see under star plastic is a data line which is defining your stress and strain as a function of LODI that is defined as a star user defined field. So as the value of the LODI is -1, is defined in the compression. When a value is 1, it defined as a tension. So on the right hand side, what you can see is the uniaxial response of the compression followed by the tension. So this is a very useful functionality of Abaqus that we have added in Abaqus 2022. In terms of the material, we have the new material model added, that is valency Landel, and that is available in Abaqus Standard. Is a hyperelastic material model, and it could be used for any material which is nearly incompressible or compressible in nature, like the rubber. And so the main feature of this material model is it is defined by specifying uniaxial test data, or optionally you can also define the volumetric test data. And main advantage that this model produces the specific data exactly similar to model model. So model is there for a long time, and you must be knowing that the model represent your tension and compression data exactly like the test data that you input for this hyperelastic material. But the problem with the model is that either it will represent the tension side or the compression side. It does not really represent the both sides at the same time. Okay, so let's look at here. So this is a material model that we have added, valency Landel. So here what I'm showing is that the solid line is the predicted material behavior, and the red dot is basically showing the test data that is the input. So what you can really see here is a very good correlation in terms of the test data and in terms of the material behavior prediction in Abaqus. Now, if you compare with model on the left-hand side, what you really see is so here this is the test data dotted line, and what you see, the solid line is represented by the model. So here what is you see the tension side is represented perfectly fine, but the compression is left out. So if you basically want to capture the compression side, so the tension side is left out. So model is very good as far as either tension or compression side is important, but many times you have tension and compression both together, and that's where that particular new model would be very useful. And another enhancement that we have is related to an isotropic pressure-dependent plasticity that is available in Abaqus standard and explicit. In Abaqus, we have these material model like the Drucker Pager and the crucible foam for quite some time. And what we have done in this particular the version is we allow to use the Drucker Pager and the crucible foam along with the Hill plasticity, and that basically allows you to capture the anisotropicity. And this improvement gives you the flexibility to calibrate and capture better the multi-scale material, like the layered composite material structure that you have. And additionally, it gives you enhancement in Abaqus explicit to improve the calculation of stable time increment based on the material effective modeling. Moving to the next enhancement in Abaqus 2022. So here it's related to the node tension and compression elasticity. This particular feature is already available in Abaqus standard, and so here this actually models material that either you can say, okay, you don't want to model tension or the compression, specifically like the rope, wherein it gives you the stiffness in one direction. So in this kind of situation, this material model is very, very useful. There have been many requests to extend these functionality to Abaqus explicit, and that's how we have done here. So you should be able to use these material model in Abaqus explicit, and here what you can see that this is Abaqus standard run and this is Abaqus explicit run, and both the run has been compared, and it shows a good agreement for these behavior. Concrete, and the next enhancement that we have, I'm going to talk about, is the concrete damage plasticity. And you must be aware that concrete damage plasticity is there in Abaqus for quite some time, and that provides the general capability for modeling concrete and other material which is quasi-brittle in the nature for monotonic, the cyclic, and dynamic loading. But this material model was not available for the beam element. So based on the many requests, especially from the architecture and the civil engineering side, wherein they have the beams and columns, typically they model with this beam element. And with the support of the beam element for the concrete damage plasticity, you should be able to model your structure, the concrete structure, with the beam element. And this is available both in Abaqus standard and explicit. And the keyword that is as a concrete damage plasticity. So here what you see is the response of the concrete damage plasticity model under uniaxial load cycle, tension, compression, tension. Okay, so next what we have is the plasticity correction. So the main purpose of these enhancement is to provide you the estimate of the plasticity of the model without using elastoplastic material properties. So what you're doing is you are still using a linear elastic material model, but it can estimate the extent of the plasticity it can experience, and specifically is applicable when the plastic deformation is very, very localized in a small region of the structure. It shouldn't be used when you have the large plasticity in the structure, and it has a very specific application, and it's typically used in the durability analysis for life prediction based on elastic solution, and that's where it adds a lot of value. So it can be used for concept design optimization workflow, and is based on the Neuber and the Glinka correction rules, and these functionality has no effect on the solution because this is a kind of the new output that you have and typically used in the durability analysis. And this must be used with the isotropic material model. So if you look at these correction on the left hand side use a number correction. So this straight line is representing linear elastic material model. So it really doesn't know where the plasticity begins, and it crosses the plasticity yield stresses, it goes up. And with this number correction, what does it do? It basically, you have a two triangle, so it moves down so in such a way that the area of these two triangles are the same. There's a little bit difference in the Glencar rules, wherein it sets the actual elastoplastic strain energy density as equal to elastic part of it. So here's one of the example. This is an automotive chassis component, and here the multiple run have been done. On the left hand side, this is elastoplastic analysis, wherein elastic plastic data, star elastic, star plastic have been used, and what you see here is the Mises stresses. And on the left hand side, this is a linear elastic analysis. No plasticity data have been used, but with this new functionality of the output, you say, I mean, you can actually have this plasticity correction. So here is the number related output and the Glencar correction related output, and what you really see here, the correction, the values are the matching with the complete elastoplastic material model. And this particular enhancement is related to the time-based strain rate filtering. So you must be aware, especially in the Abaqus explicit, when you're running the highly transient analysis. So there is a possibility of the high level of noise, especially when your material properties are rate dependent. So at this point of time, now you have some additional options for filtering out these noises. So here now we have two options to filter strain rate to evaluate the constitutive response of strain-dependent material. The first one is star material as rate factor. So they define the constant filter factor, and it was also available in the previous version. So in this version, what we have done, we have given another option as rate time. So this introduces this options gives you an option to define time-based the filter. So this new time-based filter provides you the more robust filtering, and that is not sensitive to the time increment used in the analysis. So what you see here on the left-hand side, that so this is just comparison between the two different option that is available. This is the a previously available option, and this is a new option that we have provided. So this represents a simple one element stretch test for rate dependent material with very small strain with a very small time increment. So you can see the time increment very, very small. So here what you see is that the new option is sensitive enough to show you the strain rate sensitivity with a different strain curve here, whereas the old option, you cannot really distinguish between these two strain rate. Now coming up to the yield stress extrapolation. So as you must be doing the elastoplastic material in your analysis, then you must be aware that whatever elastoplastic material point that you define, specifically star plastic, so it basically assume the plasticity constant at the end of a data point that you defined. Okay, so now with this new option, you have additional way of taking it up. Okay, so you can specify this yield stress to extrapolate it linearly. Okay, and it affects only the extrapolation of yield stress with respect to the equivalent plastic strain. Constant extrapolation is still used with respect to other independent variables. So here, if you look at the keyword, so what you see is star plastic extrapolation the constant is still default, but what you have, the new option is a linear. Okay, so let's take some example here. This is the plasticity data that is used in the elastoplastic material model. So these are stresses and this equivalent plastic strain. So you have defined point till this one. So by default, what happens is beyond this point, it assumes this plasticity constant is a pure plasticity, perfect plasticity. Okay. But this can give you a lot of numerical issues, specifically if material is experiencing any strain beyond this one. And this is challenging. It may give you non-convergence many times. So what we have provided that it can be extrapolated linearly. So this sometimes some kind of the stiffness it will provide, and it will help you running your analysis without non-convergence. Of course, the case should be taken that the plasticity is the localized, not at the bulk level here. Okay, another one as another enhancement is related to the result mapping for the shell element extrapolation. And a couple of the releases, we had the external field was used for the mapping the results. So what we have done in this version is we have unified this one and extended to map the result through thickness of the shell element. And this can be done for a homogeneous shell as well as the composite cell. So here what you see is this is the source element and this is the target element. Specifically for homogeneous shell, you don't need to have the same element density. It can be different. Okay, and it supports the mapping of displacement, orientation, stresses, and plastic strain. So you can actually map from the source element to the target element. So here these features are very useful, especially when you wanted to basically carry on your analysis by mapping these variables. But if you have the composite cell, then the source and the target mass has to be the same. However, the integration rule can be different, but if it's a composite, it has to be same. And moving to this particle technology enhancement has been a long time, almost more than 10 years. Abaqus has introduced the technique to model SPH, smooth particle hydrodynamics, and then discrete element method and the KLM were in use for especially in case of airbag and so on. So this has been in Abaqus for quite some time. And this version, what has been done is there's a significant architectural enhancement and unification to this particle technology in Abaqus Explicit. So the idea is to give you more robust, unified architecture for the particle methods wherein the tracking of these particles are involved. So it has improved the performance. And if you look at this example wherein you have the turbine flow, you have the fan blades, you have the liquid flowing, and there's a contact. And in this newer version, so it shows the improved parallel robustness. It shows you the performance improvement more than 20%. And this is a kind of the improvement that you would see in Abaqus 2022. So now this was more of the mechanics and the material side. So let me move to the contact. So here I will begin with this. I will begin with this evolving contact feature edges. So in Abaqus Explicit, in a couple of the releases, we have been actually developing and improving this feature. So what used to happen is, these perimeter edges were detected at the beginning, and those are actually used in the general contact domain. Okay, and then later on we also introduced that there may be some edges, okay, which is being formed during course of analysis, which was not there at the beginning of analysis, and those were actually kind of giving some non-physical behavior, and that was introduced in the last couple of few version from now. And but what is happening is as you are adding more and more feature to account for the contact, so it basically gives you the penalty in terms of the performance. And so in this version, what we have done is there's a accuracy improvement and the performance improvement, and we were able to achieve that the penalty on the performance should be less than 10% of the computational time. So now, because of this achievement, we made this particular the feature default in Abaqus Explicit. So if you look at this particular example, okay, so here this is deformation of the sandwich plate under blast loading. So there are small, there's a heavy deformation at the center, and the new feature edges are being formed during course of the analysis. And what used to happen in the previous releases as a default behavior, newly formed the feature edges were not there at the beginning, so it's not accounted, and there are non-physical behavior were seen, and that will be no more the case in the newer version, because by default this newly evolving feature edges are being accounted in the contact in Abaqus Explicit in general contact automatically. So this is something about contact, and we have also done very nice enhancement for general contact by enabling the dynamic allocation for general contact. What used to happen, general contact is there in Abaqus, in Abaqus Standard, in Abaqus Explicit as well. So this is more on Abaqus Standard. In the previous version, what used to happen that there is a large static allocation of internal contact elements and the nodes, and this happens at the beginning of the analysis. And typically, the most of these static location remains inactive, and that gives you the penalty in terms of the performance. So performance is affected, and sometime the error message was occasionally issued if static allocation was not sufficient. So idea here in 2022 is to remove this large static allocation at the beginning of the analysis and make it more dynamic as and when these contact patches are coming in the contact area to modify dynamically, and that has made it 10 to 20% performance improvement. If you look at the example here, there are a variety of different problems have been tested for this performance improvement, starting from the bonded plate to toe, the pipe coupling, disc brake, and so on and so forth. So you will see the performance improvement varies from the 5% to the 40%, and that has been a really phenomenal achievement in terms of making the general contact more and more usable and more robust as well. And we have another enhancement in terms of the contact, that is step-dependent interaction for general contact. So you must be aware that the general contact in Abaqus Standard, this is defined as a part of the model data. At the beginning, it's defined, so whatever you define it remains active for all the steps. But it has certain implication, because if you don't need after a certain time, still those calculations are performed, and somewhere the performance is impacted. But if you look at this contact pair, we already had option to remove these contact pair in chosen step and reintroduce it with star model change. You might have already used this one, but now these functionality have been extended to general contact. But of course, this this keyword is different. You need to use star contact exclusion in a given step, and that's where you can control the pair of the patches which you don't want in contact in general step in a given step. So here is some simple example is a forming analysis. You have the punch, you have the part, and it comes into contact, and later on you want to do the spring analysis, so you want to remove the contact, and that's what you can do it with the general contact now. So we have these another nice enhancement as far as the contact is concerned. Here we have the contact involving beams with non-circular cross-section. So what used to happen in earlier version and in Abaqus Expos that if you have the beam-to-beam contact, so for contact calculation, it used to consider as cylindrical. Now in this new version, we have made it much more realistic, more physical. So here, if you look at this the wire plot representation of the two different component, more or less the beam, and this is the rendering of the profile. Here you have the rectangle cross section, you have the hexagonal one is inserted and the rotated. So you can clearly here you can see as it's rotating is capturing the real physics of the shape and profile of this the beam, and now you can use it for more realistic performance as well. So now coming to the high performance computing, as time goes on, the model is becoming bigger and bigger, more and more details. Now you have multi-million degree of freedom models to be performed, and that's make it more mandatory many times to use HPC. So let's look at the terminology of HPC before we look into this enhancement. So in any HPC, you have a nodes, and you may have multiple nodes actually, and these nodes would be connected with the switches. And if you look at the node, you have the socket, and these sockets are nothing but the processor, and within this socket you have the multiple cores. Okay, so this is how, and then you can also attach the GPU here, and this is all about this the hardware architecture of HPC. Now coming to the hardware side, you have the two configuration. One is a SMP, another is a DMP. SMP is nothing but shared memory parallel. So here what happened is you have a single node here and a single executable process with a multiple threads for the execution. So what happened is it is a single processor, and the data communication between these threads are using the shared memory here. If you look at the DMP, which is distributed memory parallel, so here you have the multiple executable process that is shown in the red, and that's running within their own memory shape. And here what is happening, the data action between these processes are via MPI. Okay, this is how you have the DMP, and of course you can have another node, and data actions will happen with a switch and MPI as well. There's another in-between configuration we call is hybrid message passing. So here what is, you have one processor wherein you have the shared memory, and you can connect it with, this is SMP, wherein you have the shared memory. But if you add another node, so this data action is happening with MPI. So this is kind of the hybrid in the nature. You can have the different configuration. Here you have the two processor in a node. Here you have the one processor in the node, and there's another. You have the four processor in a node, and you can have the multiple node connected, racked on top of each other. So performance and the scalability have been improved. I mean, over the time, and still the development is going on to make it much more robust. I mean, much more faster. So these particular model have been run on the multiple nodes and the multiple cores. Is a huge model. Specifically, this is basically try to see how it could be scale up. Specifically, it is element more element focused model. If you look at, here's 21 million elements, here 28 million nodes, and about 86 million degree of freedom is a huge model, and it's being run on AMD Abaqus 64 core processor, and it has been run on the different numbers of the cores. Here you have one node, each node has 128 cores. As we are increasing the number of nodes or number of cores, so you would see almost nearly linear scaling, and this is being done in a DMP. So what you can see is that you can use thousands of core and still it can give you the good performance enhancement. This is specific to Abaqus explicit. Okay, and yeah, so here if you look at this is another example wherein this is a drop test of the phone, and this is a explicit dynamic analysis. The phone is dropped from a height of 1 meter on the rigid floor, so you have a contact, you have the fraction mechanics, you have the non-linearity on built-in, and what we can see in terms of the scalability is as you are running on the multiple cores, you can reduce the runtime. So this is one node wherein you have 128 cores, your runtime reduces. If you're using double the number of cores, and once again you double it and double it. So what you can see is the scalability of Abaqus explicit continues to improve, and the larger number of cores are now accessible. So great number of the cores and thousands of core for the fully featured phone model with active contacts and nonlinear material behavior can be used to scale up this run faster and faster. Now the same model have been run on HMP and the DMP. Now you can run on the both MSMP, DMP, HMP. So here is the relative performance between the DMP and HMP, the same the phone model. So here is a number of cores starting on 28 to 448, and what you really see that as you move on, the more number of cores, so the improvement with the HMP is more and more. Okay, so why HMP? Because the data exchange is reduced, so you will see relatively better performance in HMP. We have some enhancement related to Iterative Solver. So let me give you some a brief about the Iterative Solver. This solver is typically used when you have very huge model, multi-million degree of freedom with relatively less non-linearity, and which requires huge the memory, and that's where iterative solver are typically used to scale down the runtime, and these solver have been improved over the various releases. In 2017, the new hybrid parallel solver was introduced, and as we move on in 18, the new improved robustness and performance was improved, and then it started supporting the Lagrange multipliers and the MPCs. So this iterative solver is becoming more and more generic, including many features for performing the huge model faster and faster. And then we also improve the performance for large model for distributed coupling, which was not supported earlier. We included that. And now in this 2022 version, we support unsymmetric problem. So problem like wherein you have the contacts, the high friction values, which make your system unsymmetric. And these are the use cases wherein you can still use our iterative solver and make you run much faster compared to your direct path solver. So this is one example of this particular feature. This is the engine model, and here the 80 CPUs are used. So this is the direct solver, direct path solver, and this is iterative solver in 2022. And if you look at the wall clock time here, and you look at this hours, 11 hours. Now this can be done in 1.5 hours. So the scaling factor is performance factor is 7 times. And if you look at the total wall clock time, so here it took 11.2 hours. Now you can do this with 1.72 hours. Gives you the performance factor of almost 6.5 times. We already have this cloud computing in the place. So this cloud computing is a browser-based interface for running Abaqus jobs and managing the Abaqus data on the cloud. So you can take advantage of running in the cloud. So you can run on the multiple configuration. You can choose 4 core to 144 core at this point of time. It gives you access to various versions of Abaqus starting from 2022. It has a high performance storage, and it has inbuilt a visualization in place as well. And you can use either token-based or the credit-based compute licensing. So many times what happens is you have a surge in the requirement, and let's say you want to run a huge model instantaneously, and maybe the infrastructure is not there in terms of the hardware or the software. So what you can do is you can go to the cloud computing, and you can access these many number of cores, and you can use those many tokens. So this gives you so much more flexibility because it does not demand the commitment of those many number of cores or the tokens for running this analysis. This is mainly using the resources as and when it is needed. So this is one quick demo that I have. Let me run it through. Yeah, so here you have to basically log into the cloud computing, and then what you need to create the simulation. You can choose the title, you can give the description of the job and just say okay. And what you need to do is you need to drag and drop your input file from your local machine. Here we are just drag and drop, and it may take some time depending on what is the size of your input file. Once it's uploaded, you can create the job. So here, let's say that you can run it. You can choose what type of licensing you want, the token based and credit based. You can choose what type of analysis, and you can choose the number of cores from starting from 4 to 144. And you can also choose the version of Abaqus that you want to run. You can choose the result format, whether it's ODB, etc., and start running here. And while it's running, you can look at all the files. You can do the job monitoring, and these things you can very well do it. And as you move on, this job monitoring, you get looking all the files, the status file, the message files. You can look into this one. Once job is complete, you can open and inbuilt post processor there in cloud as well. So this gives you very much flexibility in terms of scaling up your analysis as and when you require more resource in terms of hardware or the software. Here are a couple of enhancements that I have included that we did it in Abaqus CAE. So in Abaqus CAE, you should be able.
Sorry, Mahendra, to interrupt you. We are 45 minutes down the session.
Okay, sure. Thank you for reminding.
Yeah.
Okay, so you can include this orthogonal material property. You can use in Abaqus CAE. You can have Young's modulus and the Poisson ratio in different direction. And we have extended this visualization of beam profile, that is channel and head beam profile, while doing the post process. And another interesting feature that we have is you can specify coordinate system in the query in Abaqus viewer. So this feature was available during our pre-processing, but this has been extended to the visualization module. And what you actually do is whenever you're doing querying the node, distance, or element face normal. So here on if you see at the bottom, you can choose the coordinate system. So you can have a local coordinate system for querying these parameter in the place. And I would like to summarize with this slide that as part of the continuous development of Abaqus, we are committed, and there is a continuous development process going on for Abaqus structural simulation technology to address high-value industry workflow at a very rapid pace. And here we have I've presented some of the chosen functionality enhancement, but there are many more specifically related to the linear dynamics, fracture mechanics, and so on. So the complete list of this enhancement you can access in the release note of Abaqus 2022 documentation. So I will request you to go through for the full complete list of enhancement in Abaqus 2022. So with this one, I would like to conclude this webinar. So I would like to take up any question if you have. Thank you very much.
Thank you so much, Raghavendra. So you can, if you have any questions, you can type it in the chat box. So meanwhile, we can start off with the questions that we have received, Raghavendra. So the first question we have received is, what should I do to activate dynamic allocation for general contact?
Okay, so this dynamic allocation, which basically improves the performance, okay, and that is actually activated by default, so you don't need to do anything as a default feature now.
Okay.
Yeah, next question.
Yeah, I hope that helps. So we have received another question is how to access cloud computing.
Okay, yeah, so this is good question. So the cloud computing, you need to have some kind of the subscription. So I would request you to connect to your local, you know, I mean, local distributor. We are here in your area, so you can reach us and we can tell you what are the different options and the subscriptions are there. It need to be subscribed.
Thank you, Raghavendra. And we do have one more question. So for plasticity correction, do I need to define elastic plastic data?
Okay, so yeah, so the fact that why we have this feature is that you don't need to have elastoplastic data to be defined. So there are newer, correction. So that basically kind of gives you the estimate of the plasticity when you don't have elastoplastic material data. Okay, so that's the advantage. You don't need elastoplastic complete data. You just need to have elasticity data, and there are certain correction based on Umbur and all that will give you the estimate of it. I hope this will help you.
Yeah, thank you, Raghavendra. So